Good evening, everyone. Welcome to the February edition of OWASP Vancouver. We're very happy to see you here, and we have 3 talks for today. We're starting with Dylan Ayrey, and I apologize if I butchered your name, Dylan. Dylan is the CEO of Truffle Security, formerly a security engineer at Netflix, and focuses on open source security tooling and security research. He's the author of the open source Trufflehog tool, and has presented on a wide range of topics, including AppSec, cloud security, SSL certificates, and more. Dylan, by the way, I remember watching your, I think it was in either besides Las Vegas or the AppSec Village talk last year, but I think GCP permissioning, it was pretty good as well. But today, Dylan is talking about the trouble with secrets.
Thanks, appreciate the intro. I think that was actually DEF CON Black Hat 2 years ago, so that was in 2020. But yeah, GCP permissions are their own can of worms, and I'll be talking more about that in a couple of weeks on some Google podcast, I think. So cool. if you're interested in that side of things. So yeah, I'm basically going to talk about secrets today. I'm kind of the secrets guy now. I wrote this open source tool a while ago called Trufflehog that finds secrets that people leak out in source code. These days, like my introduction mentioned, I'm a co-founder of a company that basically makes open source tooling to help find credentials. And so I think it's really cool now that that's basically my full-time job, is basically making open source tooling for folks like you to use for bug bounties or for in-house security teams to help find credentials. So when I say secrets, what do I actually mean? Well, basically, what I'm referring to are API keys, the credentials that give you access to different cloud providers. So on the left there, that's an Amazon key that gives you access to the Amazon cloud. That is an active key, so I encourage people to play around with that and see what it leads to. But basically, like these cloud providers, they give you access. At the end of the day, they give you access to 2 main things. They give you access to data stores where you can store and read data, and they give you access to compute to be able to process that data. And these credentials are the gate to allow you to do those things. So they give you the ability to download data. They give you the ability to run compute, to process and interact with that data. The 3 main cloud providers are up there: Google, Azure, and AWS. There's some other ones, but those are the main ones. And you think, that's a pretty tractable problem, but the reality is when we throw in all of our SaaS vendors on top of that, there's a million of these freaking things, and all of them use API keys that interact with them. So the glue that holds all of this together are these keys, and as it turns out, we're not that good at keeping them secret. They leak out all the time, and I'm going to go through a couple of fun different ways that we've found them. Ways that you can reproduce, ways that are easy to reproduce, that can make bug bounty money, and also go through some of the open source tooling to do so. So the first way I'm going to call out, I don't know if folks are familiar with Grey Hat Warfare. Grey Hat Warfare is a website that popped up a couple of years ago now. Basically, they aggregate open buckets, cloud provider buckets, that they're able to find and scrape from the public internet. What a bucket is basically, it's just a place where you can store data programmatically. So like Amazon and Azure and Google Cloud, they all have their own ways of managing buckets. But basically, it's just a place kind of like Dropbox or like Google Drive, but for programmatic access, for saving a file and for accessing that file. Grey Hat Warfare basically scraped the entire internet and found as many of these buckets as they could possibly find, and then found all the ones where you can download the data out of them, where it's not locked down, where it's fully open. And they provide it in a search where you can easily just go through the 500,000 Amazon buckets that they've found, or the 60,000 Azure buckets they've found. They aggregate some other interesting data too, like URL shorteners and stuff like that. But for this purpose, we're just going to focus on buckets. What we did was we basically took a small sample of these buckets. I think we maybe took 2,000 of them, right? So it wasn't that many in context of how many buckets they have. And we pulled all the data out of those buckets looking for API keys. And I think, we were expecting that, that we might find some. I don't think we were expecting the hundreds of keys that we ended up finding from these 2,000 buckets. But I think the scary part is that, if we're talking about an Amazon bucket, we go through all the data in the Amazon bucket looking for Amazon keys. Those keys in that bucket can then lead to other buckets, right? And then those other buckets have access to their own set of data, and you end up with this kind of worm effect where you start with a single bucket and you find Amazon API keys that could take you to other buckets, right, or other Amazon services that contain data. And then you can use those keys to access that data to find more keys, to find more data, to find more keys, to find more data, and you end up with this sort of spidery effect. And what's more is it's not just Amazon keys that we were finding. You start with an Amazon bucket and you could actually find keys to all kinds of SaaS providers. So maybe it's access to private repositories, maybe it's access to other clouds, Google Cloud, that kind of thing. Maybe it's access to somebody's Sentry or New Relic or whatever it is. We were able to find hundreds of keys to all these different providers that are warehousing some form of data. And the data that those other providers are warehousing themselves have their own sets of keys. And you end up with this really scary worm-like effect where you start with one basically public thing with some keys that are accidentally exposed. And before you know it, you're moving laterally through cloud APIs, accessing more data, getting access to more cloud APIs to get access to more data. And you end up compromising entire environments in some cases. And if you ask me, where the future of security is going, I think this idea of like endpoint lateral movement, which has been, has been the golden standard for hacking for years, like your Metasploit, that kind of thing, where you drop a malware framework on a laptop and use it to jump to another laptop. I think that's becoming more difficult, like especially with immutable infrastructure and the way we do deploys these days, serverless architecture becoming more and more popular. I think that type of hacking is going to become less popular, but this type of hacking is going to explode. It's super easy to do. You find these keys, and then you don't leave any artifacts behind. You don't have to drop malware anywhere. You're just literally jumping from one cloud API to another, and all the APIs are on the public internet. So you never have to do this from a private network. You never have to put an implant anywhere. All you're doing is just chasing keys to data on public APIs. So if you ask me, like, where the future of data breaches is, I think it's this, because it's really like it's becoming more and more popular as multi-cloud and SaaS becomes more popular, and it's really easy to do. So another way that these keys get exposed, I think, for 10 years, people have talked about the way source code can accidentally get leaked out when your .git directory gets exposed. Basically, what this is like, I think in general, source code is very leaky. Like we see it all the time, right? We see it in the headlines when Apple's next firmware or whatever gets dumped on GitHub. But one way that's really common for source code to get leaked out is if you're developing a code repository using Git, all of the artifacts of your code repository, all your revision history and stuff like that, that gets stored in something to Git object store. And all of that data is contained in the .git directory of your current working directory. And so if you just take all of the data that you're developing and you throw it onto the internet, onto a web server, sometimes you accidentally throw that folder up as well, the .git directory, which contains all the artifacts for the source code, all the old revision history, and about 50% of your code is actually buried in the past in older versions, where those older versions can contain keys, even if your latest version doesn't. So we've been talking, like, there have been people presenting on this for 10 years. This is somebody's blog post, 2 years ago talking about this .git directory problem, but it's been a problem for a long time. And you'd think we're making some progress on it, but, I think like literally an hour ago, right? I went through the Alexa 1 million, right? The most popular websites on the public internet, the 1 million most popular websites, just looking for .git directories that were exposed. And I found dozens. Right, dozens of the most popular websites on the internet accidentally leaking their source code out. This is a screenshot I literally took an hour ago of one of them. So this is very much still a relevant problem. Also, anecdotally, like 14 minutes ago, I guess I made the deck. I edited the slide 5 minutes ago, so maybe 20 minutes ago at this point, I saw somebody on Twitter tweeting about a .git directory exposed. So this is very prolific. And how does this tie back to secrets? Well, the tool that I mentioned before, the Trufflehog tool that I wrote a couple of years ago, specializes in ripping through source code and finding keys really fast. And so you combine these two things together, and all of a sudden you're able to go through code that was never meant to be made public, and you're able to go through all the revisions of that code, and you're able to find these cloud keys to kick off the same type of attack that we just talked about before with buckets. And so, I think a lot of focus has been put on public GitHub, but you take it just one step further and you say, well, what are some other ways you can get access to code? You find keys are actually way more common, because there's tons of people looking for keys on GitHub, but not many people are taking it this extra step, but it's still super easy to do. So in that vein, what we did is we open sourced the Chrome extension like a month ago. And all this does is it just passively goes through every web page that you browse, and it pops an alert box if it ever finds an API key on the page you're browsing. And you might be saying, like, that's like, when would that ever happen? Like, when are you ever going to be browsing, like, checking the weather, and all of a sudden, like, an alert pops up saying there's an Amazon key on? Like, that's not going to, well, that's exactly what happened. Like, shortly after I wrote the Chrome extension, went to weather.com, and on the front page, there was an Amazon key, like an access key and a secret right there that could access cloud APIs. You might, the next question is why, right? Why is there an Amazon key there? Isn't there like CORS restrictions or whatever that prevent weather from talking to Amazon? Well, the reason why is actually a lot of these cloud providers encourage front ends to talk to them. They open themselves up. They have fully permissive CORS. They either wildcard themselves or they reflect back the origin header, and they want other websites to interact with their cloud APIs. And this is encouraging these types of API keys to actually leak out in static resources like JavaScript. And so I found this Amazon key. I reported it to weather.com. They revoked it, but you could just go on archive.org a couple of versions back and find the dead key, because the internet never forgets. But this Chrome extension has found all kinds of stuff, and it's just literally just looking at another form of source code. And so this is another, like, what's the bar to find these keys? Like, it's pretty low. And the impact, I've talked to some companies recently that have seen 7-figure losses because an Amazon key accidentally leaked out, an attacker found it, and then they spun up a bunch of crypto miners and ran their bill up. So the impact of these keys is enormous, and the bar to finding them is on the floor, right? This is like super, super easy for anybody to do. The Chrome extension is available in the Chrome store if you want to play around with it. Let's see if we can lower the bar even further, right? We've lowered it to like Chrome extension. We make it even easier. This is a Google Cloud key. It's the typical format for a GCP key. It's got a bunch of different fields and stuff. It's in this JSON blob. When we look for secrets or detect secrets, usually we look for unique signatures to that specific key that we can search for. So in this case, two things that make pretty unique pairing. The first is on the bottom, this client X509 cert URL. It's a very unique string, very specific to Google keys. And the second is when we pair that with the begin private key piece that goes with private encryption keys, those two strings together pretty much always will produce a Google Cloud key if you're searching, like you're not going to get any false positives from those two pairings. So literally, again, I did this earlier today. You take these two strings, type them into Google, and by the fourth page, you could find a real key. Like that's really where the bar is. Like, you don't need technical ability to find these things, and the impact for them is enormous. It's in the 7 figures. So that's the status quo that we're dealing with today, and I think it's only going to get worse as we get more cloud integrated and as we get more SaaS integrated. So what can we do about it? I think is the next logical question, and that kind of speaks to some of the open source tooling that we have coming up that we're going to be releasing. One of them that we're really excited about is very soon, in the next month, we're going to be augmenting open source Trufflehog to be able to not just say if it finds a key, but it'll also validate to see whether or not that key is still active. And the reason that's super important is today, when you pull metrics on how often a code base has an active key to an inactive key, 75% of them are inactive, right? They're buried in the past, they're old, they're not useful anymore. And it's difficult to put that burden on a developer. Like, if you alert them every time you find something that looks like a key, most of the time they're going to find something that's not an active key, and they're going to get pretty fatigued. So introducing that to Trufflehog, I think, is super exciting. We have it running in a private beta now. We've given it to a couple of researchers. In about a month, we're going to give that back to the community. It's going to be open sourced, and you're going to be able to easily tell whether or not these keys are active. This screenshot, though, you might be looking at it and say, wait a minute, what does it mean to have an active private key, right? Like I can generate an encryption key now. Like what does it mean to be active or inactive? Well, we open sourced another tool relatively recently that speaks to that, and it easily tells you whether or not a private key is potentially sensitive. The way we did that, if folks are familiar with certificate transparency is a public ledger for all SSL certificates that get minted these days. So if a certificate authority creates an SSL certificate, that certificate authority is required to log that certificate in certificate transparency. So we went to certificate transparency and downloaded every single one of the billions of certificates that are logged and pulled the public keys out of every single one of those and indexed them in a database. And then the second place that we looked was we went to public GitHub. Folks probably are familiar with the fact that you can upload a public SSH key to GitHub. Did you know you can query any user on GitHub and download their public SSH key? Because I didn't know that a couple months ago, but when I found that out, we queried every single one of the 34 million active users on GitHub and downloaded all of the public SSH keys that we could. And then we indexed those as well. And what we ended up with is a database of billions of public keys that we know pair with sensitive things that can either log into people's GitHub accounts or can be used to encrypt SSL traffic. And we open sourced a tool called Driftwood that allows you to instantly take a private key and do this index lookup and tell you whether or not it pairs with somebody's GitHub account. So here you have an example of that. You feed it a key. In this case, this key is actually encrypted. And we, just for fun, we also open sourced a piece of Driftwood as well that'll try a bunch of passwords on the encrypted key. I think the word list we open sourced with it is like a couple hundred long or something. It's not a very fancy list, but it does actually work on a fair number of keys that we found. It'll decrypt the key if it's encrypted. It'll take that private key and it'll extract out the public component. And then it'll do this index lookup and instantly tell you whether or not it pairs with a GitHub account or it pairs with SSL. So that tool is called Driftwood. It's available on GitHub today. And soon we're going to be natively building that into Trufflehog. So it all kind of pairs together. So how do we deal with this? Well, you know, the first step is you need some sort of policy, right? Like if you're a company, I should say. If you're a bug bountier, you know, just enjoy, right? Like these things are all over the place. But if you're a company and you're trying to deal with this problems, the first step is you need some sort of policy or alignment on where you want your keys to be. So whether that's, you know, HashiCorp's Vault product or AWS Secrets Manager, whatever it is, right? You need to say, here's where I want my secrets to live, and then make a little wiki page or whatever that documents that. So that's step one. And then step two is you need some sort of enforcement mechanism that's constantly going through and looking for these keys. Because I don't know about, you know, the companies that folks on the call are from, but at previous jobs, you had thousands of engineers that were coming and going and had to learn all the policies, and then a year and a half later, they're already on to their next job. Like, you need some sort of enforcement mechanism that's making sure that those keys aren't leaking out. And that's where some of the open source tooling that we're putting out helps with. And we're going to continue to improve those tools and put out more features and capabilities, and continue to focus on, you know, verifying keys to make sure they're active and focusing on signal and things like that. And then the last step on the slide is to cry a little bit because it's a really hard problem. All right. Well, that's all I have. Any questions I can answer for folks?
Yeah, pardon me. I do have a question. I was wondering, you know, how was it exactly that those SSH public keys were found? I thought that it was, you know, privately, you know, secured under a person's account, or was it publicly available on the web somehow?
Public SSH keys that you upload to GitHub are not private. Every user's keys can be downloaded. You can do it through the API, and you can do it through the web interface. So they make no assurance of privacy there, and it's documented in their API for how to download them. So we just literally followed the API and downloaded them all.
And public keys, I mean, they're called public keys by definition. You make them available to others. They're often used so that people can use it to encrypt something and send it back to the owner who has the private key, right? So, you know, what you want to make sure for the public key, you don't want to, you don't want to keep it confidential. You want to expose it to as many people as possible, but you want to make sure that you can guarantee the authenticity. So if the source is not trustworthy, then you could be downloading, my public key, but it's not really my public key because someone could have modified it as source, right? That's where, certificates come in and all kinds of other stuff.
Right.
One
right.
interesting consequence of this is, having all these public keys. We've found several private keys that were in repositories totally unrelated to the user that paired with it, right? So some user uploaded a public key that went with, let's just say, a large company and had access to lots of sensitive repositories. We found a private key in a totally unrelated repo that was for some tutorial. And that user had downloaded that tutorial, taken the private key that was there, and then taken the public key from that private key and uploaded it to their GitHub user account at some point, right? They just followed the tutorial. And you'd never be able to connect those two dots if you didn't have this sort of database that had indexed them all. But it was super cool after we indexed them that we were able to connect those dots. So I definitely encourage folks to play around with it. Feel free to throw it, all kinds of keys and see what you can find.
To me, it still sounds a little bit weird. Like I can't think of a use case where GitHub would expose the public keys. Like I understand like secure email as MIME kind of scenarios, but this is not the keys that's used for that. Like this is the keys that are used for like signing Git commits and like cloning repositories, committing, that kind of thing.
Actually, Git commits are signed with GPG, so that's a different key system. Right. So it's even more like I don't know either. I imagine there is a use case. We didn't dig into that. We didn't figure out the reason. But yeah, I agree with you. Like I'm not actually sure why those public keys are available for download.
Hey, I have a question. Hey, Dylan. On your second advice on constantly running scans to discover these keys, my question is how effective is using certain out of the box services, so to say, like AWS Messy, or I think Datadog also has a feature to a beta service to look for secrets, matching the regex patterns. And I think so does GitHub Enterprise. So how effective are these services, to be utilized to discover secrets that's out in public?
Yeah, I think some of them are more mature than others. Like some of them have, at the end of the day, they all have like a set of different credentials that they detect, and none of them have a complete set of every SaaS vendor out there, right? So that's part of the problem, right? It's like GitHub will spend some time building out a secrets detector for, I don't know, I forget, like 50 to 100 secrets or something like that. Well, there's certainly more than 1,000 SaaS providers out there in different ways for your keys to leak out. And so, those tools are helpful to an extent, but if you're a bug bountier, you can often find secrets that aren't covered by those tools and find credentials that are leaking out outside that purview. So, it's a good question. I think we could use all the tooling that's being provided to us, but it's, in my view, still easy to just think of a little bit of, exception to it. Another example is like sometimes credentials are base64 encoded. So at some point we did an exercise to go through all the base64 we could find on GitHub, decode it and look for credentials. And we found a bunch of really sensitive credentials that had evaded, whatever other native. I think Amazon and GitHub actually have a partnership where if an Amazon key ever leaks out on the public internet, it'll actually get revoked. Well, if you just take this extra step of base64 decoding, you can find Amazon keys that weren't revoked. And so, the short of it is, like, I think we're in our infancy in being able to detect and remediate this problem. And I think vendors and open source tools are going to get better over time. But right now, we don't have a perfect solution yet.
Seems like that kind of partnership is not unique to GitHub and AWS. I know AWS also does that for example, for Slack webhooks. Like if you post or if you publish a Slack webhook in a public repository, it's going to get revoked pretty quickly.
Yeah, I think it's interesting where like the driver of that is Amazon, right? I don't think like GitHub, not that they want people to leak keys out, but I don't think it's as sensitive to them as it is for Amazon to realize their customers are having $1 million losses. And so Amazon is worried about this, and they're going out and forming all these partnerships to try to, prevent that from happening. But yeah, absolutely. Like there's definitely a ton of resources that AWS has invested in that space. Not all the SaaS providers players out there are investing that much. And so, we're in the infancy of this problem, and I see it only evolving as time goes on.
Right. Can Trufflehog work as a commit hook? Like, can you basically do that scanning on incrementally on like the changes on your code base?
Yes, it can. And we've actually been working on a couple new features we're going to be pushing out soon that'll make that even nicer. The thing is, like, when we talk about like the full software development lifecycle, like scanning code is important, but it's like only the first step, right? The next step is you have some Jenkins thing or whatever that pulls in your code and does your build. But Jenkins itself has access to secrets, right? Like, it has its own secret store that aren't checked into code. And then you have people logging to standard out the secrets that came into Jenkins. And then you have your Jenkins logs that are exposed. And then you have Jenkins packaging stuff up and shipping it off to Artifactory, right? And if it takes one of the secrets it just used to packages that up by accident and sends that off to Artifactory, now you've got Artifactory with secrets that aren't checked into Git. And so this problem, the being able to scan commits in real time, that's important. But then you have all these other secondary artifacts as a part of your SDLC process as well that also need coverage. And that's kind of how we're thinking about it. Like, ultimately, we're going to open source tooling for like every piece of that puzzle to be able to get complete coverage for all the places that could have this issue.
I know one of the checks that the tools that look for secrets can do is kind of entropy analysis, like for keys or secrets that don't have a specific format or is something unique that is not very popular and that tool doesn't recognize. How noisy do you see that kind of scanning is?
That's good for a bug bounty or not good for much else. Because to your point, like, if you use entropy detection, you might at best case get like a 1 in 10 situation where you might find a key 1 in 10 times, which is fine if you're a bug bounty, right? You can dig through like 10 noisy junky things of just UUIDs and things that aren't actually secrets. For the one, you get your payday and that works. But if you put that in front of a developer, they're going to get so frustrated with it so quickly. They're going to turn it off. They're going to ignore it. They're going to do whatever they need to do, never interact with that thing again. So that's the way I look at it. The entropy detection, I included that when I wrote Trufflehog way back in the day, because I wrote the tool for bug bountying, sitting on a couch making some passive income. That was the main use case. I wouldn't recommend using that like defensively or to put that in front of your engineers or anything like that.
Makes sense.
Amran, is I guess next in our agenda, is that your piece, or are we going to go to Bruce's piece?
I think I'm going to go next. I'll be really quick. My part is not that long. Awesome.
So I guess we'll go right into it. So Amran is going to explore the invisible source code vulnerabilities, which is what CVE 2021-42574, and then there's the 4269. And Amran,
don't get me to cite that number, please.
Yeah. Awesome. And Amran, do you want me to do a quick intro on you? I guess I could. Amran is one of OWASP Vancouver's board members. Also, Amran, you're part of DC 604 as well, and Amran does excellent work helping further the cause of application security and security in general in Vancouver. And I'm proud to work with you, Amran, in the OWASP Vancouver board and help increase the voice for application security. Amran also works at TaskTop. And Amran, what else would you like to say about yourself?
That's probably it. Like, I've been in the security game too long. As you can see, I've lost all my hair because of that, but that's what I'm blaming. But yeah, had quite a number of quite different roles, and lately have been focusing on application security, which I think is a fascinating field. And so today, I just I'll be upfront. This is obviously not my research. I just came across this. I think this research was published sometime in the fall, November or so, and I came across it, and we did a little exercise at TaskTop to basically understand what does this mean to us and how does this impact TaskTop. Is there anything we need to be doing about this? As a result, kind of, I've built a little bit of understanding what's going on, and basically today I wanted to share some of that. So it's invisible source code. It's basically a couple CVEs that was identified and published by researchers. So this is not something that was being actively exploited at the time. So quite different from Log4j story. I haven't heard of any cases where any of these have been seen in the wild, but it's kind of at this stage, it's sort of a theoretical exercise that probably all of us who deal with application security to some extent need to be aware of. And they both deal with Unicode, which like my understanding of Unicode is very minuscule, but what I do understand, it is an extremely complicated thing. Like there's so much in the Unicode, and most of it, as I said, I don't understand, but that complication is bound to bring some issues, some of which will be security related. So the first of the CVEs, which is probably the more interesting one, is related to the use of Unicode control characters. Unicode control characters, they're characters in Unicode, or I should say code points in Unicode is, I believe, the more proper term, that are generally invisible, like they're not displayed by themselves on the screen when you view the document or view the text, but they control the display of the text. So they basically affect how other text around them is being displayed. So you can think about this. So new line and tab, probably not a great example, but in Unicode, there's also a whole bunch of them, and some of them are related to the left to right, right to left text directionality, because Unicode obviously supports, and one of the selling features was support for all the different international alphabets. And so it has to be able to support the alphabets where you write and read from right to left as opposed to left to right. And so the control characters is at the core of that support, and being able to basically tell the text editor how to display the text that follows. So there's a whole number of them, and they work in a slightly different way, but essentially there are control characters in Unicode that support the way text is displayed on the screen. And this brings me to my first demo. And the first demo is really simple. So I basically have this text file. I open it in a text editor that knows what Unicode is, and it says OWASP Vancouver. When I go and actually display what's in that, and this is basically the same file. When I go and actually display what's in that file, you see that it's completely different. And the reason for this is in the beginning of that file, the first character basically tells the editor to display this text in a different direction, right to left. And when that happens, the text editor, which majority of the IDEs are essentially Unicode supporting text editors, obliges and displays the text completely differently. And that brings us to that first CVE, which essentially uses these directionality control characters to create a difference between how the source code is displayed versus how the source code is going to be interpreted by the compiler. So this is my second demo, and this is basically the core of that first CVE. And as I said, don't make me cite the number because I don't remember. And even in the editor, you can see somewhat that something weird is going on, because you see this if statement. I mean, it shouldn't be part of the comment, but it definitely is displayed like it is part of the comment. And so if I didn't have the syntax highlighting, the way I would read this as a human being is, okay, there's a have access flag, have access is false, so this shouldn't execute. And if we check what's happening, it actually does execute. And at the core, and maybe we can take a look at the file in the editor that has no idea about Unicode, you see that in effect that code is actually within within the comment, but through these control characters, it was made to look like it's outside of the comment. And so that's basically using those control characters to make text look differently to the programmer who would maybe read this or do a code review on it, versus how it is being interpreted by the compiler when it converts it to something that's actually being executed. So that's the first CVE, and let me check. I think there was a question or something. You would think that control characters would be flagged, i.e. visual alert would be present in IDE. So it wasn't the case at the time when the CVE was published. Let me show you what this file looks like in Visual Studio Code, but this is after an update that they did after the CVE was published. So here you can see, let me make this bigger. Here you can see they basically highlight them in this red and basically say, hey, this is the 22E control character of Unicode. So you kind of can, and even like changing the way the text is displayed, but like going back to the whole idea, this is not an obvious thing to do, because ultimately, if this stuff was within the string, you probably wouldn't want it displayed this way. You would want it displayed the right to left kind of thing if you need to support one of those languages. But yeah, so going back, Mark, to your statement, at the time, majority of the IDEs were not doing that. Nowadays, some of them started doing that exactly for the reason of kind of dealing with this issue. I quickly check the chat. SAS tools like SonarQube, SonarCloud does flag and fail on scan. Yep, thank you, Dana. Well, I'll talk a little bit about like a couple of things what different vendors have done to deal with this. But again, at the time back in the fall, SAS tools compilers were not doing, and IDEs generally were not doing any of this. The second of the CVEs has to deal with homoglyphs. Homoglyphs are basically Unicode characters that look the same, but in effect are different characters. And this is a screenshot from a homoglyph generator. I've just entered OWASP Vancouver, and basically you can see that there's a whole bunch of different options how you can change the string using different characters, but it's still going to look very similar or exactly the same in many cases. So I'm from Russia, so this is dear to my heart, because like we in Cyrillic alphabet we have letters that look exactly like the Latin Roman letters or Latin letters, but they are different letters, the Russian letters. And so if I was to change this A to Russian A, then basically it will look the same, but it's a different string. And so the second CVE is basically using that distinction to the advantage, and sorry, this is the wrong one, and to create a security issue out of it. What's happening? Sorry, just one sec. I don't use Atom a lot, you can see that, but it's one of the few editors that still is okay when you do a demo with this. Okay, maybe I'll reopen this folder. There we go. No, nothing happened. Come on, show me that thing. Oh, there we go. Okay, there we go. So I've got two source codes here that essentially look very similar. So I've got demo3 good that basically calls for some external dependencies that's named demo3 dependency to check access. If it returns true, it should print bingo. If it returns false, it shows you shall not pass. And here it looks on the surface, at least, that it's basically the same code. So let's firstly try to run it and see what happens, and then understand why that happens. So I'll do demo 3 good first. And as expected, or maybe not as expected, but we see that with demo 3 that function returned false, and so we supposedly don't have access. But in the case of the second file, we do have access. So what's happening here? What's happening here is, if you look carefully at this letter Y, you see that like even in the editor, it's slightly different color. And what I've done is this Y is replaced with a different character, Unicode character, that looks the same. And so this dependency is completely different from this dependency. So we have, and you can see it in the file tree, there's 2 files that are named very similarly. So if I open this one, sorry, let's open it here. I actually don't know which one is which, but we can probably, there we go. So these are, although the names look the same, these are 2 different files that do 2 different things. And again, the idea is that somebody who has access to your source code potentially can change it in a way that that does something else that would be hard to detect for another developer or somebody who's doing the audit or a code review of that code. Okay, let me quickly check chat and we can probably wrap up. Okay, Mark, maybe I basically this is all I wanted to show. I had some demos, and the last thing that I wanted to do is basically bring it back to all of you to say, what do you think? What do you think is the so what, the answer to the so what? Like how does it affect us? What should we be doing? But before that, I want to mention a couple of things. So firstly, now a lot of the static code analysis tools highlight these issues as errors. Some of the compilers, for example, Rust compiler, and if you want to see a response that was really good and timely to these CVEs, take a look at the advisory page, and I'll post all the links just once I stop sharing my slides. But take a look at the advisory that the maintainers of Rust have published. They're basically started to throw compile errors for source files that include these control characters outside of strings, because again, there's a legitimate use case for the text directionality if you use them in strings that are basically displayed back to the user. So outside of the strings, the compiler starts throwing compile errors and doesn't compile source code. So I'll pause here, and I hope that people will have questions or comments. So Mark, I've seen you had some comments. If you want to unmute and voice them, that would be good too.
Or it could just be my ignorance here, but like, is there a legitimate use case for the presence of multiple Unicode characters or differing Unicode characters, like say on the same line? Could there ever be a legitimate use case for that? And in the case where you had the control characters, they were simply not displayed. I mean, they were there, you put them in there, they were simply not displayed. So I think that's a failure on the part of the code editor. But as you said, they have since revised the code editor, and they've now made that much more visible. But my question is really, what else is the code editor hiding? And shouldn't code editors be at the molecular level, showing everything and hiding nothing?
Possibly. I don't think I have the answer to that, but I'm curious what others think.
Well, I suppose one thing I do know the code editors do is like there was a specific thing that you can enable so that like the arrow key thing that you would do for anonymous functions in JavaScript, like it would appear differently. So perhaps the text editor would try to present things nicely from the coder's standpoint.
Yeah.
And as a result, it would hide some of these vulnerabilities.
Yeah, exactly. Unless it's like a plain text editor working in plain text mode, which nothing is hidden. Anything that's not in plain text mode is going to have some sort of a prettification based on some characters.
Right. So is there, other than the control character example, a legitimate use case for mixing Unicode characters?
I see some links being shared. I don't know the answer to that, Mark. I don't know if anyone knows. If anyone does, feel free to speak up. Thanks for sharing those, Amaran. So, any other questions, comments, anything else on this one for Amaran?
What about the testing tools? Like I think Dana posted something about some of the more popular tools are actually catching this, but like ultimately that's where the reliancy is, right? Would you not think that would absolutely be flagged to see something that's pretty, because we can't come up with a legitimate use case. It seems pretty uncommon. It should be flagged.
I think it should, and to me, this is a perfect use case for static code analysis tools that tend to be quite noisy in other use cases. But this is I think you can detect reliably and alert on them. Absolutely.
Okay. Should we continue to our next guest for the evening?
There's a question about recording. The recording will be posted on our YouTube channel.
Yes.
And I'll find a link to that in just a second.
Awesome. So is Bruce on the line? Bruce, are you there?
Yeah, I'm still here.
Excellent. There you are. Excellent. So let's move on to that segment. So I guess I'll introduce Bruce. So Bruce is going to talk about multipass, managing your infrastructure access. Bruce is a software engineer at Infra, which is an identity and access management for infrastructure companies, starting with Kubernetes. They create a platform for developers to securely manage access for their entire infrastructure. So with that said, Bruce, I'll pass it over to you.
Thanks. Thanks for being here, everybody. This will go pretty well with the secret talk we had earlier, so that's good.
Awesome.
All right, and you can see my screen, just the slides. Perfect.
Can I see the fifth element reference there?
Yeah, I tried to sneak in more references, but I couldn't really get enough relevant screenshots. All right, welcome to Multipass, Managing Infrastructure Access. By the end of this talk, my goal is to provide you with a general understanding of modern best practices for infrastructure access control. This talk is going to be more geared to the blue team kind of defending your infrastructure rather than the red team using Trufflehog to find people's access keys. You should be able to take what you learn in these next 30 minutes and apply it to your own infrastructure to identify any weak points. You'll also have a basic knowledge of the tools needed to act on those vulnerabilities. Getting started with the basics, the first question on your mind, I'm sure, is who is this guy and why should I listen to his opinion? So here's some background on me. In short, I'm a software engineer with a background in security and access control. You can see some of the companies I've worked at on the screen. I worked in Seattle at an ill-fated augmented reality company called Magic Leap. There, I worked on their authorization systems that allow internal and external applications to communicate with each other and manage authentication. I've also worked for a while in Vancouver at a single sign-on company called Ping Identity. There, I worked on an identity federation server used by about half the Fortune 100 companies to manage employee and customer identities. Currently, I work at a startup that's based out of Toronto called Infra. Our goal is to make infrastructure access simple. For the last 8 months or so, I've spent most of my time at Infra trying to find better ways to manage infrastructure access. Today, I'll share some of those insights with you. Before we start drilling down on the problem and some approaches to mitigating your risk, we should start at the basics. Infrastructure is a broad term. It refers to the structures or facilities that comprise a larger system. Common examples of infrastructure could be like roads, bridges, sewers, or the electrical grid. Well, in our case, kind of obviously where this is OWASP, we're talking about computer infrastructure, computer network infrastructure specifically. This could be a physical server running on premises, a hosted virtual machine, Docker containers, a Kubernetes cluster, or any resource hosted on a cloud provider. In a more granular sense, infrastructure also refers to whatever is running on that computer network infrastructure. So that could be continuous integration or deployment pipelines, or application services making calls between each other. As with any good security lecture, we have to do the classic scary security horror story to set the stage. This goes along pretty well with what was mentioned earlier in Trufflehog. I'm going to take you back to 2019, when a series of unfortunate events at Samsung resulted in unauthorized access to an AWS account with allegedly internal source code used by their Bixby services. What was the source of this problem? An unintentionally public GitLab repository that contained the private GitLab tokens of several team members. Some of these credentials were for an AWS account that had access to hundreds of S3 buckets containing logs and analytics data. The scariest parts of stories like this is that it could happen to any of us. The team members clearly thought that they were working in an internal repo, and they didn't realize that it was accessible to the outside of the corporate VPN. They probably also didn't realize the scope of privileges that the tokens in this repo had. According to one study, 46% of S3 buckets have misconfigured permissions. So it's hard to get this stuff right. It's best to design infrastructure access control from the ground up to ensure these scenarios aren't possible. So what's the problem with many infrastructure access control systems in general? Unless you're starting from scratch, you've probably got a very complex distributed network. Access to each of the separate systems in your network may be managed by the resource locally. For example, the users that may access your Kubernetes cluster could be a list of usernames and their associated tokens. This makes it extremely difficult to understand who has access to what, audit what different users are doing, and monitor for potential bad actors. So let's go through some classic solutions to the infrastructure access problem. The naive and most simplistic approach to access control is to create accounts with static credentials for each component of your infrastructure. This is tempting on a small scale because it requires the least amount of overhead. Most systems will have some kind of username password-based authentication mechanism you can leverage here, so it's pretty easy to do. In the worst case, static credentials means creating one account for each system in your infrastructure, then sharing the credentials between anyone that needs to access that infrastructure, maybe in a spreadsheet. A slightly better case is manually creating an account with appropriate privileges in each system that someone needs to access, and then storing their credentials in a password manager such as 1Password, which is administered by the organization. Static credentials can be managed on an individual basis, but they're best to avoid. They have many issues. It's difficult to manage provisioning and deprovisioning accounts. There's no observability into which accounts the user has access to, especially when they leave the organization. The chances of unauthorized parties maintaining access is very high because you can't actually see what accounts they were given. It's also difficult to monitor. There's no central point of access, so it's difficult to see what's happening on your network. Finally, it's harder to keep these credentials in sync. So if a user goes and changes their credentials, now there's no valid place for an admin to go access their account or revoke their access. And finally, I guess it's kind of also important to note that the experience around static credentials is just terrible. Typically, it means finding the right person to talk to and asking for access manually. Similar to static credentials, you may also choose to create static keys, which can be presented in request to infrastructure resources as a form of proof of authentication. So that's like the API and access keys that we saw earlier. This is a popular approach for machine-based authentication as opposed to user access, as it's convenient to be able to make these requests directly to an infrastructure destination simply by including the secret key in the authorization header of your request. The basic approach here is to create different secret keys for different clients and then distribute them to the appropriate parties. When a request is made with an issued secret, it is assumed to be the party that the key was issued for making that call. That means you get a small amount of auditability. A challenge with this approach is that it's difficult to manage secret key validity. If a key is compromised or should no longer be valid, it may be difficult to track down where it was actually being used, and it could have been being used in multiple places. This approach also means storing secret keys directly in the calling environment, which we saw with Samsung is not a secure form of storage. One solution to the problem of controlling access keys is securely storing them in a secrets management system, such as HashiCorp Vault. This offers many improvements over manually distributing keys and trusting clients to store them properly. With a secrets manager, you create a central form of access control that stores your secrets encrypted at rest. And by creating this bottleneck, you can manage access to secrets easily and monitor who is using them. It also creates a central source of truth, so you can easily revoke and change secrets without redistributing them to all your clients. Great, problem solved, right? Well, maybe not. Once the secret is retrieved from the secret storage by a client, it is sent over the potentially untrusted network, and we rely on the client to securely manage that secret while they're using it. These are some assumptions I know I'd rather not make, so it's best to avoid this also. We also still don't have a direct link between who is retrieving the secrets and how they're used afterwards. Finally, we all know we can't fully rely on secrets, so we need a second factor in our access control to make sure only authorized parties are calling infrastructure on our network. A good candidate for this would be to only allow access to our infrastructure using connections through our corporate VPN. In some cases, such as accessing an internal service without authentication, the VPN may even be used as the only form of access control. In this scenario, we put a lot of trust on the VPN. If there's one weakness in our network that allows a bad actor to gain access, then they could potentially gain access to many systems within our infrastructure. Don't get me wrong, a VPN is a valuable tool, but a more segmented approach is preferable. Now that we've covered the most basic forms of access control, let's move on to the ideal ways to tackle infrastructure access in 2022. We'll need to develop a model that outlines the shortcomings that we just went over and provides a better alternative. Our solutions will also need to account for the fact that modern organizational infrastructure is distributed. Some infrastructure will be managed on premise, while other infrastructure will be ephemeral and hosted in cloud networks. Our infrastructure is going to be created and destroyed ephemerally, and it needs to be easy to manage while it's going through those ephemeral processes. So let's get started by planning out our ideal model for infrastructure access. We'll be aiming for 6 key components in order to address the shortcomings of the approaches we previously looked at. The first pillar here of our access system is going to be identity. This is probably the most important component for us to address. Without an identity attached to all the interactions on our infrastructure, we can't build any other components we need. All actors on our network, be it users or machines, need to have a known characteristic which identifies them. There should be no anonymous traffic on our infrastructure at all. Now that we know the identity of the party using our infrastructure, we should also be able to see and review what they are doing exactly. And this brings us to auditability. Our infrastructure will need to have a system for monitoring current and past activity. Current activity should be able to be easily flagged for suspicious behavior or unexpected changes in general. We should also have a log of past infrastructure usage that can be reviewed in the future to trace an identity's path through our infrastructure. As we just saw with the static secret model, a common weakness of infrastructure access is that the attack window to actually use credentials is way too long. So a preferred scenario for us would be for credentials to be as short-lived as possible. This means that any access we grant to our infrastructure will go away quick, and if it does happen to be exposed, then we don't really have to worry about a huge window of vulnerability there. Tokens issued to actors modifying our infrastructure should be refreshed periodically if access needs to be extended rather than a really long window of validity. In the static username and password model, managing identities on our network quickly became confusing and could not scale as demand for access to our infrastructure increased. All changes to our infrastructure should be automated also for reliability. This ensures that as our infrastructure is ephemeral, things can be created and destroyed quickly and easily. Second to last here, if someone gains access to our internal network, they shouldn't have the keys to the kingdom, like we were speaking of with the VPN. We need segmented infrastructure access to ensure that incoming requests don't have access to everything until they are proved they are authorized to perform that action. And now finally, as I already touched on, when I specified that our access should be automated, our infrastructure access should also be dynamic. This means that new infrastructure on our network is automatically available to any parties that should be authorized to access it. It also means that if a party's access to our infrastructure needs to change, whether that's escalated access or reduced access, then that's reflected quickly and with minimal interruptions or overhead. So let's dive into each of these separate components of our ideal infrastructure access control. Where identity will be the basis of the rest of our infrastructure access control, it makes sense to start here. This is a pretty dense aspect of our system as it will potentially be publicly exposed. It relies on trusting third parties such as Okta or Auth0 and needs to have secure authentication system. When it comes to infrastructure access, we have two main types of identities that will be on our network, users and machines. This differs from your typical user-facing application that is only concerned with user identities. Ideally, most of the traffic on our infrastructure will be machine identities communicating with each other, but there will still be some cases where a user identity is relevant. Say a systems configurations engineer or a DevOps engineer need to access our infrastructure to make modifications. You can also imagine scenarios where a developer needs to troubleshoot a deployed system on our infrastructure. So we need to account for this. In this case, single sign-on and trusted sources for user identities are the best way to manage users. You've probably seen a similar principle in application access control. At most large enterprises, when you are hired, you are added to the organization's central Active Directory of users. This allows you to sign on once using an application portal such as Okta or Ping Identity and gain access to all the applications you need to do your job without managing many different accounts. We should follow this same principle for infrastructure access. We also get a single source of truth for infrastructure access by relying on this single sign-on provider. That means that for users, we should allow third-party authentication, be that Okta or any other open identity provider, that allows us to manage our users in that single source of truth. Relying on a trusted identity provider also means we can easily access attributes about the users, such as their roles or groups they belong to. These attributes can allow us to dynamically change their access and generally manage coarse-grained access easily. Relying on a user identity provider also means that we can add multiple factors to our authentication, which is fancy. For example, we can configure Okta to require a one-time code in order to proceed with the authentication. Now that we've covered users, machine identities are going to be a bit more for us to implement. There isn't as convenient of an external authentication mechanism as there is with single sign-on for users. There's still, of course, many widely used and useful machine authentication mechanisms we can leverage. The first and most important piece of machine identity is their certificate. Machines can present certificates in the process of mutual TLS to show that they're in possession of a key pair signed by a trusted authority, which serves as proof of their identity. Certificates also allow us to ensure that machine communication on infrastructure is encrypted end-to-end and non-reputable. In the case of both users and machines, we should also make sure that devices accessing our infrastructure are known and managed. This means keeping track of devices managed by your organization in an inventory database using a unique identifier, such as that device certificate. If you don't control the device, ensuring access is securely managed is pretty difficult. All right, now that we're through that pretty dense part, and we know who's on our infrastructure, we can set up a system to keep track of what they're doing through maintaining an audit log. This will allow us to be aware quickly if an actor is doing unexpected things on our network. It will also allow us to perform a detailed analysis after any incidents that result in unauthorized access to our infrastructure. Adding an auditing system to your infrastructure is a bit of an undertaking. To have a system that monitors and logs all your infrastructure access, you have two options. The first option is to funnel all your traffic to different infrastructure resources through proxy gateways. And the other option is to add an agent to each infrastructure destination that observes interactions and audit logs them. Both of these options will send the information they collect to a central audit log service for storage, review, and analysis. As we mentioned, modern infrastructure is ephemeral, being created for as long as it's useful and then destroyed. So too should infrastructure access be ephemeral. The key problem with our static secret storage controlled through a secret manager was that the secrets within the encrypted secret vault are long-lived. We were giving them out to our clients and trusting that they wouldn't be compromised. If these long-lived secrets do get compromised, rotating them is a pain. Due to their long-lived nature, clients don't expect them to change, which leads to painful problems and unexpected downtime when they are rotated. We should make everything in our infrastructure access system as short-lived as it possibly can be for its given use. This includes authentication credentials, access tokens, role assignments, and generally privileges. A good pattern to follow here is to have some form of slightly longer-lived credentials. So we're still stuck with the API key, but we use it to exchange for some more short-lived credentials with more sensitive permissions that are valid for a short amount of time. Though this model of issuing short-lived access means that we can ensure that changes are propagated quickly also. So once the client presents that access key and we give them the shorter-lived credential, we can check exactly what permissions that client actually should have at that time. But then in other cases, in the case of stateless authentication, like a JSON web token, a signed token is considered proof of a given claim. By making these tokens stateless and short-lived, we can ensure that they're accurately reflecting the current attributes also, similarly to the exchange model. We script and define everything as code in our modern infrastructure. So following this model for identity provisioning and access definition means that our access control is easily maintainable, clearly defined for reviews and auditing, and requires a minimal amount of oversight. Using a well-defined access control system means that we can identify when a new identity is provisioned and then give them a predictable amount of access to infrastructure based on their attributes. A major convenience of this is simply adding an identity to your source of truth, like the Active Directory or Okta, is the only action needed. The rest of the access and infrastructure discovery will be automatically reflected. A simple example of this is in the product I work on. You can define infrastructure as code that specifies an identity or group, and also define which resources they can access and what privileges they should have in those resources. Managing this YAML file in a GitOps style workflow means that you can easily observe changes being made and automatically deploy these changes to your infrastructure when it's merged. Different parts of our infrastructure should not rely on an external system to completely manage access control. Relying on requests coming from a corporate VPN means that fine-grained access control becomes nearly impossible. In order to control fine-grained access on an individual request basis, your infrastructure should be segmented. The standard approach to segmenting a network is to use a public-facing proxy to control access to private infrastructure. This public-facing proxy is known as a bastion host. The sole job of this bastion host is to work as a hardened interface to your infrastructure. So it will validate the identity and authentication of an incoming request only, pretty much. That's its only job. Then if the request is valid, it sends the request on to its final internal destination. Also an important note to call out is that proxying requests is preferred to port forwarding because it doesn't require decrypting the traffic in between. With our secure infrastructure access in place and easy to maintain, our last concern is that changes in the system are reflected quickly and accurately. We can achieve this through a combination of our previously mentioned goals. By making credentials and access on the system short-lived, we have also improved the agility of our system. Through requiring frequent checks with the central issuing authority, we can be assured that any changes we make on our system propagate quickly. If the central access control authority is the only source of authorization state, then we don't need to worry about the system getting out of sync. Our infrastructure access system is also dynamic in its ability to be automated. Through a repeatable configuration defined through code, any new infrastructure will be automatically controlled with the appropriate authorization checks. And in an ideal system, clients using our infrastructure also have a way to check which resources are currently on the network they have access to. So say a user is using like a CLI to SSH into whatever infrastructure. If we have a dynamic system, they should also be able to query that and see what infrastructure they could actually SSH into without asking somebody manually. Great. Now we understand all the different pieces of our infrastructure access control, but how do we put this into practice? We need a blueprint that we can follow to get started. A great resource to begin planning your model is Google's BeyondCorp paper. This paper was originally published back in 2014, but it's been followed up with additional papers that give context to deploying their design, migrations, and user experience. It also gives concrete examples of the steps Google took to secure their infrastructure access. Additionally, it also gives context around how to test these changes before you roll them out so you won't get any downtime. The core goals in the BeyondCorp paper are reflected in the attributes of an ideal infrastructure access system that we just outlined. They have defense in depth through many layers of authorization, single sign-on for authentication, PKI for encryption, and use context to determine access. The overview is only about 5 pages long, so it's a pretty easy and quick read. I'd really highly recommend it. All right, we've gone through our whole model. We know the different pieces we need, but more concretely, let's look at some tools we can use. There's a lot of tools in the DevOps space, and many of them focus on the problems we just covered. To wrap things up, I'll highlight some potentially useful tools for you. The biggest and most well-known player in this space is, of course, HashiCorp's Vault. Vault allows you to store your secrets, whether they're for infrastructure access or otherwise, in a centrally, securely encrypted enclave. In order to access the secrets stored in Vault, a client must present a valid credential, and then they'll actually be given access to the secret. This is a great tool for simplifying your auditing of secret usage and having a central point to change a secret when need be. It also integrates with HashiCorp's other tools, such as Boundary, for more dynamically controlled access. Next up, we have Okta Advanced Server Access, or Okta ASA. It's a product from an identity management company that you probably already use, being Okta. The focus of ASA is to allow managing access to infrastructure for the identities that you already have in your Okta directory. ASA focuses on access through SSH and RDP. Generally, it focuses on infrastructure that isn't ephemeral. The downsides of the ASA tool, in my opinion, are that it isn't well suited for modern cloud infrastructure, such as Kubernetes, and it's also kind of got confusing enterprise pricing. But if you're already using Okta, ASA is definitely a tool to look into. Now moving down here to Spiffy, the Secure Production Identity Framework for everybody. It defines a framework and a set of standards for identifying and securing communications between application services. It's a project from the Cloud Native Computing Foundation that you probably already know. Spiffy lets you bring identity to your infrastructure by creating a standard interface for different hosts to communicate between each other. This is commonly done through X509 certificates that follow a predefined format. There are several implementations of the Spiffy standard. One that you may have heard of or even worked with is Istio, the service mesh, which allows for Spiffy communication on different nodes in your network. And finally, last but not least, we've reached the part of the presentation where I shamelessly promote my own company. At Infra, we're building an infrastructure access management platform for users and machines. Our product is designed to fit into any infrastructure access control model, but currently we're focusing on simplifying access to Kubernetes and cloud deployment infrastructure. It allows you to bring your existing user identities from identity providers such as Okta and define their permissions and infrastructure destinations dynamically. It also integrates seamlessly into your existing tools, so you can continue using kube control commands to manage Kubernetes while your access is actually managed through Infra. Currently, we're in closed beta, but if that seems like a tool that's useful for you, please request access and we'll get back to you. Thanks for your time. hopefully I've given you some actionable ideas that you can use to improve your infrastructure security. You can follow me on Twitter at _BMACD. And feel free to check out my company's website because we're actually hiring right now. So if you're into this stuff, give us a look for sure. I'll take any questions now if anybody has any feedback.
Thanks, Bruce.
I have a question. What sort of like tutorials or like resources are there online for this sort of a thing that you would recommend?
Yeah, it's not like really one silver bullet in this case, in my opinion. Like I touched on, I do really like the Google Beyond Corp paper. I'd recommend focusing on one problem at a time. So first, securing infrastructure to infrastructure access through something like Spiffy, and then maybe afterwards kind of building on just whatever you have available. So like I said, if you have Okta, ASA is a great tool. Teleport is another great option you can use to dynamically control access to SSH, and I think they also have database connections.
All right, cool. So in a way, we could use your slides, basically what you said, as like a guide to looking at the relevant documentation for all these things and putting it all together. Yeah.
Yeah, I don't think there's really like one specific tool you can just drop in and have all this stuff in one go, unfortunately.
Fair enough. Fair enough. Thank you.
So yeah, I see there was a comment in the chat. The Azure Key Vault was not mentioned in the presentation backed by Active Directory. Was there a reason? I guess that's a good key management solution as well if you're in Azure.
Yeah, for sure. This just wasn't mentioned because I don't have as much familiarity with Azure.
Got it.
Most of my time is on AWS.
Awesome. Let's see if there's any other questions or comments in the chat here. Yeah, feel free to, and for the audience that are here with us, feel free to just unmute yourself and ask the question directly if you like as well. I don't see anything else.
Thanks, everybody.
Awesome. Well, thanks very much, Bruce. Really appreciate it. It was an excellent talk. And thanks everybody for attending this month's OWASP Vancouver chapter meetup. I guess I'm around the next event that's coming up is March 9, that with OWASP Vancouver with VIPSS and ISACA as part of the Application Security Sector Day. Now that is going to run from 9 a.m. to noon, if I'm not mistaken.
Right. Yeah.
Excellent. And I'm supposed to share with you the link to the survey one more time. Betsy asked me, and I am going to do that. Just let me see here. Are there any other links that are worthwhile? Yeah, I'm going to share a link to the survey for this month's meetup. And I guess we also have that general survey about the OWASP chapter. I don't have the link to that one handy. Let's see if I can. Imran, that's the February 7th. Would you mind sharing that link? Imran, do you have the link for the general OWASP survey handy by any chance? I just shared the survey link in the Zoom chat.
I'll see if I can find it.
Cool. Yeah, we would appreciate, we're trying to improve the Vancouver chapter to help serve you better. And your feedback would be quite important in helping us achieve that. So we would take, if you could take a couple of minutes and fill these things out, it would really help us to help you. And I see, Amran, you also shared our YouTube channel. That's excellent. Yeah, all this stuff will go on YouTube very shortly.
Curious question. Would there be any plans for in-person meetups coming up for this sort of a thing? Or?
Yeah, as the restrictions ease, we will certainly be visiting that. We've been taking directions so far from the OWASP global organization. They had specific directions for the chapters up to now not to go back to in person, but as things are easing up globally, that is also going to change. So we're looking at that hopefully for later this year.
Sounds good. Thanks. I'm just new here, so just popping these questions. I don't know.
And welcome, by the way. Welcome. We like new faces.
Thank you. Appreciate it. It seems very enlightening and lots of stuff to learn. I like that.
Yeah, yeah, and when we did have these things in person, we also had like a few times a year we do workshops, hands-on workshops with in group situations, and also opportunities for people to network. We tried to do networking opportunities and some of that kind of stuff online, and it's just not the same for sure. All right, I guess we could maybe wrap this up, unless anyone has anything else they want to share or discuss. Okay, well, everybody, thank you for attending our session today, and we'll see you on March 9, hopefully. Take care. Have a great evening.
Thanks all.
Thank you. Goodbye.